find it hard to think of a company that has not affected my personal life more than Intel, as I've been growing up ever since when I first saw a 486 system back in my youth. And in this case, our guest is Mutaz Haddadin, Haddadin. In particularly of interest, Ohio is the new fab that's coming online that Intel is still building out, I believe. And as such, he can share fantastically fascinating perspectives on the sheer complexity and size of this kind of program and project.
Thank you. There we go. Can you hear me? We good? Okay, great. Good afternoon. It's a privilege to be with you today. And I can tell you that we've been here on campus for a couple of days now, and the amazing talent and the interaction with the students is just mind-blowing. So this is really wonderful to see. My name is Mutaz Haddadin, and I've been at Intel for this is my 25th year. Do I switch to this?
You can use the clicker here.
Okay, thank you.
Oh, the bottom buttons to go forward. Yeah, sorry.
Okay. There we go. So today I'm going to walk through a Semiconductor Fab Perspective. The majority of my career has been at Intel in the manufacturing space of semiconductors. We'll go through my personal journey. I want to share with you my journey in the past 25 years. Then we'll go do an overview of Intel Corporation and the amazing journey that we've been on. And we'll go through the Semiconductor Fab Perspective, and that's where I spent the majority of my time at Intel. And I do want to share with you some thoughts, and we'll open it up for question and answer. So I grew up in Jordan. I came to the United States when I was 16 years old. I did graduate from high school in Delaware. I did go to the University of Delaware. It was close by. I spent my first 9 years in engineering at a company called Gore. Many of you who live in the Midwest, probably you have some Gore-Tex gear, right? They tell me that if you don't have Gore-Tex in the Midwest, you can't survive. So that's where I spent my time in manufacturing. But I really, the pivot that I made in my career and my life, I moved from the East Coast all the way out to Arizona with Intel. And it's been absolutely phenomenal 25 years. And I spent I joined in late 2000, and I was in technology manufacturing. And that was my first picture actually in 2001 in a clean room in semiconductor. Spent my time in working with the industry, with the suppliers and supply chain and developing new technologies and roadmaps. Spent some time in semiconductor standards committee, creating standards for the semiconductor ecosystem, their technical standards. And then in 2006, the company was going through a pivot, and I shifted to technology development in Portland, Oregon. And that's where I spent a good, from 2006 until 2014. I spent it in technology development in Oregon, working on pathfinding, roadmap, and capabilities for factory operations, but also automated material handling systems. I continued with the industry standards and helping Intel develop technical standards for the industry. And then I decided to change careers again, and I pivoted from technology development to supply chain. And I spent about 2.5 years in global supply chain, fab sourcing of the factory equipment. And that helped me really gain a good perspective on what else goes on at Intel in the supply chain that enables our factories to do what we do every day 24/7, and that's managing our suppliers that do a wonderful job for us. And then in 2015 through 2017, I figured, might as well just go back to school and learn more. One thing I encourage you all to do is it's never too late to learn something new and different, and also the latest academic research in the specialization area that you're in. And my specialization was large-scale system of systems, and I went back and got a master's degree at Georgia Tech. And then in 2017, I was asked to go back to technology development, and I had the privilege of leading the organization in automated material handling systems for about 5 years. And that's the team, the amazing team that continues to do the great work that you'll see here. We have a video to share with you on the work that we did there. And then in 2022, I decided to join our Ohio team and come to the Silicon Heartland and help Intel build our next generation factory here in Oregon. And I've been there since 2022, and I moved to Ohio last year. And while you're at this, I highly encourage you, get a dog, because the dog really helps you through it all. The journey has its ups and downs, but it's always wonderful to go home and have your dog greet you, and that's the best relaxing tip that I can give you all. So what do we do? What's our purpose at Intel? What it is that we focus on? It's world-changing technology. We create world-changing technology that improves the lives of every person on Earth. It's literally, that's what we do. And I think many of you have seen and used our products or the end products that our customers deploy, whether it's in the telecommunication, the computing, or the IoT and the healthcare and the energy and transportation. An average car, does anybody know how many devices are in an average car? Computer chips, typical car. Any guess? Yes? 10,000. What's that? 10,000? 2,000. I think it's because we talked earlier today. I think it's about 2,000, but hey, maybe I'm wrong. That was a number that I looked at a long time ago, but I'm sure you guys can ask ChatGPT or Google it if you guys have the answer. But that's what empowers us to do what we do every day, whether it's in the autonomous driving, whether it's in the airbags, or you look at healthcare or the energy or the telecommunication for our cell phones. Those are the devices that today are affecting all of our lives and that we use it every day. The growth, the explosion of the data that's available to us, and the growth in the what's called this silicon, I can't pronounce the word, but the level of scale, the sheer scale of what's happening is absolutely amazing, and it's not going anywhere because we continue. There's a growth in population, there's growth in devices, and everything is connected, and that generates a tremendous amount of data and information, and how we leverage and use that information to make our lives better and change every person's lives on Earth. That's the power of the data that's available to us. The demand for processing, which goes back to the growth in the data, whether it's you go in the connectivity, compute, sensing. Sensing is becoming another area where, you guys look at in manufacturing, for example, in automated manufacturing, intelligent manufacturing, all that information to make it back to the databases so you can actually do something with it and have insightful data, is that you need sensors. And that sensing technology is what enables the insights that you'll gain from all that data that is collected, whether in intelligent manufacturing or other areas that compute is deployed. And obviously there's what we do with the internet and the mobile devices. From a priority perspective, we have product leadership. You guys are all familiar with the Intel products. It's in your laptops, you look at it, and we used to have the term of Intel Inside. I think many years ago we had the Intel Inside commercials. You guys probably remember those. I remember those growing at Intel. And then the manufacturing at scale, this is where we decided as a company that we wanted to do a pivot. So for the past 4 or 5 years, we have been focusing on pivoting the company. We are what's called an integrated device manufacturer, where we basically design the products, we manufacture the products. And I believe we're the only company in the United States that does it end to end. And you'll see that in one of the videos that we have. But we decided that we want to pivot where we are offering our foundry services as an IDM 2.0. Well, basically, not only that we're going to produce the products for the Intel products, we will offer the same service to produce the products for other manufacturers that they design their own chips. At the end of it all is really the heart of what makes everything happen is the people. Anybody, and I'm going to use the example that my manager in Ohio, he's our vice president in Ohio, and he says anybody that has $20, $30 billion can build a factory. So if you got a bank account, you got $30 billion, you don't know what to do with it, you can build a semiconductor factory. But what makes it work is the people and the talent and the organization that you build and the culture that you have. And that's how the people fit into the overall picture for us at Intel. So now I want to show you a video that's going to tie all it together, but please, think about the video. You're going to hear certain things, and I'm going to go through them and through the presentation. Can you help me with the switch? It's Edge. And it's the first one. Yep, that one. Just go ahead and click. Thank you. Oh, can you do that switch?
Making a computer chip requires the most complex.
Sorry.
Manufacturing process humans have ever devised. For more than 50 years, Intel engineers and scientists have continually faced, then overcome, challenges posed by physics when the features on a chip shrink to the size of atoms. They've developed new ways to squeeze billions of microscopic switches, called transistors, onto ever smaller computer chips, many as small as a fingernail. Transistors 10,000 times smaller than a human hair that cycle up to 5 billion times per second. Back in 1965, Moore's Law, named for Intel's co-founder Gordon Moore, predicted that the number of transistors on a chip would roughly double every 2 years. Intel R&D engineers, mostly based in Oregon and Arizona, have followed the Moore's Law metronome year after year, with inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. These advances have paved the way forward for the entire industry. They are the foundation to enabling modern technologies infrastructure, including the internet, mobile computing, cloud computing, and artificial intelligence. And it's not just about silicon innovations. Intel's more recent advanced packaging inventions, such as EMIB and Foveros, allow us to interconnect together multiple chips on a single tiny package. Our focus on R&D, we invest billions of dollars every year, has been the foundation of our success and industry leadership. Once chip architects create the highly complex blueprint for new computer chips, they're sent to one of these massive semiconductor factories, or fabs, for manufacturing. Building a new fab, fully equipped, costs about $10 billion and takes 6,000 construction workers about 3 years. A finished fab generates about 10,000 jobs, 1/3 of them in high tech. A typical Intel fab requires 35,000 tons of structural steel, more than 5 times the weight of the Eiffel Tower. The clean rooms in a typical sprawling factory cover the equivalent of 4 U.S. football fields. It often takes 2 semi-trucks to deliver each of the fab's 1,200 multi-million-dollar tools. Some of these tools weigh as much as 5 tons, the weight of 3 mid-sized cars. Most Intel fabs include water reclamation facilities. 90% of Intel's water use is restored or returned to the environment. By 2030, Intel aims to reach net positive water, putting more water back into the environment than we use. Once a fab is up and running, this 27-mile automated material handling system shuttles blank silicon disks to hundreds of tools that eventually turn them into wafers, containing hundreds of Intel chips. Intel manufacturing and packaging is operating at mega scale worldwide, requiring a global supply chain that stretches across multiple continents. Once they leave the fab, computer chips are shipped to Intel's assembly and test factories, where they are put into protected packages and tested. Our assembly and test factories send our packaged chips to one of our 17 distribution hubs across the globe. Intel teams there ship almost 2 billion units a year to over 2,000 customers. Our vast supply chain includes 8,000 products and 16,000 suppliers in 100 countries. As the chip-making business grows ever more complex, Intel is one of the few remaining firms in the world, and the only one in the US that does it in-house. Design, manufacture, ship, and sell.
No, just switch back to the slides, yeah. There we go. Slideshow, that's right down here. Right there, yep. Okay. Hopefully that was insightful to you. It really just, I love that video. It was made, I believe, in 2021 or 2020. And it just takes it end to end, the entire process from the design all the way to selling the product at the end. And it talks about all the challenges and all the opportunities that we have throughout that process. And then he talked, in the video, he talked about the global presence that Intel has, which what you see on the screen. Our factories, there's the wafer fabs, which is at the substrate, silicon substrate, wafer level. Those are the darker blue sites, whether it's in Oregon, in Arizona, in New Mexico, in Ireland, in Israel. And then we have the assembly test factories, and they're lighter blue. There's some in Arizona also. There's in Costa Rica. We have I think it's over on the Asia side of the map. And also we have some future factories, and you heard about the Ohio factory that the professor mentioned earlier, and that's our next generation factory that we're building in the Silicon Heartland here in the Midwest. Our values and culture, like I said earlier, anybody that has $20, $30 billion can build a factory, but without the talent, the people, the passion, and the culture and the organization that you build, it doesn't work. The semiconductor business is a very complex and complicated business. It is hard work, it's innovation, it's uncertainty, it's exciting, but you need a very solid foundation and principles of values, and the culture that we bring to the table every day is what makes that difference. Whether it's in our customer values, our customer first, fearless innovation, the level of innovation that happens in semiconductor industry is absolutely amazing, and we'll get to talk about that in a second. The results, you have to deliver the results. At the end of the day, it's a business, and you have to deliver the commitments that you made. Absolutely, absolutely, it's integrity. If we don't have integrity in everything that we do, and at the top of that integrity is the safety aspect of how we conduct ourselves, because we are in an operating factory, safety is number one priority for us, and that's the way you come in excited to come into work every day, and we want you to leave excited going to your family the same way you came in. And that's the aspect of safety that we cherish in every day that we show up to work. Quality and also inclusion in One Intel. We are a very cross-matrix organizations and company, and there's a lot of, those organizations have to interact to make the whole machine work. And everything that Robert talked about in the video, bringing all that together, that's the one team mentality that we have in our culture behaviors. Also, Robert in the video talked about the water reclamation. He talked about how we recycle water, and we have a commitment to be net positive water by 2030. Semiconductor manufacturing is water heavy, intensive from the usage, but also there's a tremendous amount of effort and investment that we have made over the years that we are using water, but at the same time we're giving water back to the community that we operate in. Now let me shift gears a little bit more and talk about the semiconductor manufacturing. You saw also in the video, Robert talked about Gordon Moore. He was one of the founding engineers of Intel back in the 60s, and he had an observation that the number of transistors on a chip was doubling. I think initially he started with like it's almost a year, but then he revised his prediction, and it was every 2 years. And roughly that prediction has been true for the past 50 years. And I went to the internet and I found this graph, which I think really is insightful, but it only stops at 2020, so it's got a lag of 5 years there. But you can see the progression of the number of transistors on these devices. Now we're talking in billions. Now, in a little bit, we're going to talk about making those transistors, and now you're making billions of them on the devices that we manufacture. So in process technology, and that's Gordon's Moore, and our commitment to continued innovation. Over the years, Intel has continued to innovate, and every 2 years, we double the number of transistors on the devices. This is what shows our roadmap for our upcoming processes, whether it's currently we're running at high volume in Intel 7, and also Intel 4 and Intel 3. What used to be codenamed 10 nanometer and 7 nanometer, and now we have our 18A process that's going to be in high volume manufacturing in Arizona. And then on the right-hand side, that's where the future process nodes that are coming up. And there's the deployment of what's called ultraviolet lithography, and that's the EUV lithography machines. And we'll talk a little bit more. We have a video to show you about the technology that's used for to create the print. Basically, they are the printers that print the computer chips in the factory. And every process node that we go through has its own challenges. One is you're doing the scaling and the shrinking, and that's Moore's law. And then you have capabilities and features that your customers, whether it's the Intel products, our internal customers, or our external customers, where we have the foundry services, going to be asking you for those capabilities and features in that process that has basically, it's the marriage between the process technology that we're deploying and also the product design that they bring to the table. And every process has its challenges and has its opportunities. There will be the problems that you face, and that's where the talent comes in from all the engineering and the technicians in the organization and in the factory to solve all these problems. And literally, I mean, you're being challenged by the laws of physics. When you start getting to the level of atoms, literally in some of the processes, steps, you're manipulating atoms to build transistor structures. For those of you that are in chemistry, and I'm not a chemist, I'm a mechanical engineer, but manipulating atoms to build structures at the nanoscale. That's what happens in the chamber, in the chemistry chambers at every one of the process tools to build those structures. But every process you go through, because you're changing the structure of the transistors, you're changing how the design is done, that's where the opportunities and the challenges show up, and you have to overcome those. And now you're getting to the point where it's getting really hard. It's very difficult to do that at that nanoscale. Manufacturing process at the highest level. This is just an illustration to take what comes in. You start with a silicon wafer. For those of you who have seen the videos on YouTube, it starts with silicon, right? And that's it starts with the sand that they turn it into the silicon wafer. And have you seen that process where they pull the molten silicon and then they pull it like it's called an ingot? What you see, the tip of that cylinder at the top there, this right here, that's the pulling process when they pull the silicon out of the molten bath of silica, and that's where you end up with these discs. Basically, they machine it and then they slice it like a bologna slicer, right? But it's a very high precision bologna slicer that gives you the 300 millimeter silicon wafer. That's the substrate. That's what's been carrying the industry for decades. And I'll show you the transition that the industry went through from wafer size to wafer size. Currently, the industry is sitting at 300 millimeter diameter, which is 12 inches. Then you have the process materials. We use a lot of process materials, gases and chemicals. Then also you have the process equipment, extremely complicated and complex process equipment that's put together by the ecosystem in the industry. That's the process equipment. This equipment, the average cost of an equipment sometimes is $5 million, $10 million, $15 million, or $20 million just for one piece of equipment. So the capital intensity that goes on in semiconductor manufacturing, and that's why it costs $20, $30 billion to build these factories. And then you have the device design. That's where our customers design their chips that they're interested in manufacturing, or the Intel products group that design the computer chips. Then also, now you got to print the computer chip. And that's where the mask and the mask operations come in. And the mask, basically, it's a very clear, very pure piece of glass that's about 6 inches by 6 inches. And then you have laser writing machines that actually take the single layer of the chip design, and that's what gets printed on the mask. And that's what's called the mask operations that creates these basically templates for us so we can do the printing. That's what goes into the lithography tools that gets exposed by the technology in the lithography tool to print it on that disk. But you got to do this many, many, many times, because it's just layer after layer after layer, so you can build the transistors structure. So all this feeds into the fabs, and that's the fabrication. Now we have the research and development in Oregon. That's the RA campus in Hillsboro, Oregon. We have high volume manufacturing in Oregon as well. We also have high volume manufacturing in Arizona. We also have high volume manufacturing in New Mexico, but also in New Mexico we do disaggregated manufacturing, and that's for the packaging and assembly. All this has to happen. This is really what's called the front-end factory, and that's where the wafer level, then you go to the die sort process, and that's where the wafer gets diced up into the specific die, what's called a die, and it's a rectangle or a square depending on the design. That's the chip that ends up going to, that's where you do sorting, and the die gets tested, and some die is going to clock at a specific gigahertz, etc. And that's where the assembly and the packaging happens and the attachment to the motherboard. And then you end up with the products that you end up, whether you're buying it at Best Buy to build your own computer, or it goes to the client computing, or it goes to desktops, or the customers that deploy the solutions, the end solution that you end up using. So that's at the highest level. And then the customers are with you along the way as you go through this cycle. Now, I went to kind of bring it into, for you, from a study or a domain expertise that you're trying to explore, to bring it into that space. I found this diagram and I really loved it because I think it puts everything into perspective, and it outlines the specific areas of the steps of the process that I just described at the highest level. Up at the top, this is the other piece that goes on in our factories, and that's what's called the automation stack. And that's all the control systems. Basically, it's the brain of the factory. Now you have built a factory, you build it up, you put in all the facilitization, all the chemicals and gases and the ultra pure water, and now you have the equipment on the floor, you have technicians, you have engineers. Now the factory needs a brain, because it has to know what material to run when, how fast, and how much of it. And that's the scheduling and dispatching systems, which is the MES, material execution systems. That's the execute. But above this layer also, there's another layer that does factory forecasting. There's a lot of algorithms that are built that looks at the entire flow of the factory. It looks at all the equipment, what equipment is available, not available, if there's an equipment going down for a preventive maintenance. It factors all those in, and there's an engine that runs in the background that basically says, here's how many wafers you can run through the line over the next 3, 4, 5 days, right? And that gives us that forecasting capability, but that engine constantly is running to evaluate and assess the environment in the factory to ensure that we are optimizing the performance of the factory overall as the conditions in the factory change. For the most part, and you're going to see that in one of the videos that we have, for the most part, the factories are running in autopilot, 24/7, right? Now, from let me go back. From a domain perspective, this is where the engineering comes in. If you're thinking about whether it's chemistry, chemical engineering, physics, optics, electrical engineering, or you're looking at mechanical engineering or robotics, every one of these steps encompasses many, many of those careers. And I think this slide right here, which Intel put together, it tells you the domains and expertise that you have that you can explore as a career, whether it's in computer science, AI, machine learning, or it's in manufacturing, in industrial engineering, operations research, et cetera, et cetera. Now let's watch this video. It's a 4-minute video, but I do want to show you this. Go ahead. You can. It's the second one, I think. If you go to Edge. Yep, and it's the second one. Can you go ahead and?
21 years I've been reporting at Intel.
There you go. Thank you.
Amazing products and the machines that help create them. But the machine I'm about to show you blows my
For me?
mind.
Yeah, I'll wrap it up. No problem. Thanks.
This is it, an EUV, or extreme ultraviolet lithography system. It is likely the most complicated machine humans have ever built. It pushes Moore's law forward, and chip makers cannot produce leading-edge chips without it. But more on that in a moment. The EUV machine is a reality after 35 years of sustained research and development from lithography leader ASML, Intel, TSMC, Samsung, and others. Delivering just one of these tools to Fab D1X in Oregon took 3 747 cargo planes, 40 freight containers, and 20 trucks. The school bus-sized machine comprises 100,000 parts and weighs nearly 200 tons. So what exactly does this EUV machine do? Intel co-founder Gordon Moore observed that the number of transistors crammed onto a processor doubles roughly every 2 years, a cadence that has continued for more than 50 years and has long been known as Moore's Law. The more transistors and components on chips, the cheaper and more powerful they become. Chip manufacturers use lithography machines to project circuit patterns onto silicon wafers. For decades, they have kept shortening the wavelengths of light on lithography machines to print features for ever smaller transistors. In pursuit of Moore's Law, Intel engineers have produced inventions such as high-K metal gate technology, tri-gate 3D transistors, and strained silicon. Intel and other chip makers have also adopted processes such as double and quad patterning and water immersion lithography to get the most out of today's 193 nanometer wavelength light. But to make transistors even tinier, the industry needs lithography machines that use radically shorter wavelengths. This EUV machine produces light at 13.5 nanometers. Compared to today's machines, that wavelength is more than 10 times smaller.
So how does this machine work? Put on your best thinking caps, and I will try to explain it simply.
First, extreme ultraviolet light does not exist naturally on Earth, so we have to generate it. Because this tool is so large, it needs 3 floors in the fab. Its laser, about 15 times more powerful than ones used to cut steel, sits on the level below the clean room. A beam transport transmits the laser pulse up a floor into the EUV machine, where a generator fires tiny droplets of metal tin. Each droplet only about 1/3 the diameter of a human hair. And that powerful laser, flashing at 50,000 times a second, hits the molten tin. The metal vaporizes into a plasma. This plasma releases light in the extreme ultraviolet range. A collector mirror gathers the 13.5 nanometer EUV light and shoots it to a scanner, where it pinballs off extremely precise mirrors that shape the light into slits that create patterns of transistors and interconnects onto a silicon wafer.
See, wasn't that simple? Just a couple more remarkable facts.
Newer factories at Intel have ceilings 16 feet high. They are raised to 25 feet where these EUV tools rest, because it takes an overhead crane system to assemble the heavy system components. How precise are the EUV machine's optics? Here's the math. It's analogous to an astronaut standing on the moon with a laser pointer targeting the tip of my fingertip here on Earth. ASML is already working on an improved version of the EUV tool that will offer even finer resolution lithography. Intel is currently the first customer in line to receive one of these next generation machines to prepare for the Angstrom era of computing.
Isn't this mind-boggling? Hope you enjoy coming behind this
Go
door
ahead.
to see this mark.
Any impressions? I can't even, like, it's mind-blowing, really, what Robert just went through. And that's just one machine, but that is the most complex machine in the factory. So this is what Oregon site looks like. I had the privilege of contributing to building this site over the past, since 2006. But if you go inside this factory, there's another video that I want to show you, but for the time, I'll go ahead and skip it. You can look it up. It's called The Heartbeat and Blood Flow of the Factory, that shows you how we move them. I think the other 2 videos showed you how the material moves in the factory. We have all these vehicles running around. We do about 16,000 moves an hour, and that the move is considered where you pick up the box from one location, you drop it off another location, and that's the automated material handling system that does that. But this is where just for just 2 minutes, the industry has transitioned over time. Started out with silicon discs that are roughly about 2 inches in diameter, and then they transitioned to the 4-inch, then they transitioned to the 6-inch, then they transitioned to the 8-inch, then they transitioned to the 300 millimeter, which is 12-inch today. And every one of those transitions, typically historically in the industry, gives you about a 30 to 35% cost reduction. So the more space you have, the more devices that you can fit on the chip. And then also some chips are larger than others. For example, a data center or a server chip is going to be a little bit larger than a client computer or maybe a laptop chip, and that's where you can fit as many chips as you can on the 300 millimeter surface. On the right-hand side, also in the 90s, everything was done by hand in the industry. We pushed carts around technicians push carts around, they take the wafers in a box, they put them up, load them up. But now everything is being done 24/7, automated, fully automated. But in order to do that, the industry got together around 1996 or so through 2000, and they created physicality industry standards in order to enable that operation to happen in a uniform way across the entire ecosystem in the industry. So this way, when we buy equipment, we can interface the automation systems to the equipment in the same way, in a standard way, so we can do it 24/7. But a lot of the drivers behind this was productivity, but also it was safety. Because to do 16,000 moves an hour, how many people do we need in the factory to push carts? There was a lot of ergonomic issues, and the physical size is about 10 kilograms, and for somebody to repetitively keep moving 10 kilograms for 24/7, that's where a lot of safety problems were resolved and the innovation of what the industry had done. But these complex systems that you see on the left-hand side, that's where some of you are interested in industrial engineering or systems engineering or operations research, simulation and modeling, factory layouts. We spend a lot of time trying to optimize how we set up our factories such that we can maximize the output of the factories, reduce the cost, increase the velocity, and we do a tremendous amount of work in that space, working with the industrial engineers to lay out the factory in a way that gives you the optimal outcome. So I'll leave you with this one here, which is to manage all of it, especially in the automation system that I just shared with you. You're trying to maximize the site utility. That's the fundamental objective of what the factory needs you to do. They want to maximize the output. They want to maximize the velocity, how fast you get the product out the door. You want to minimize the overall cost, but also you want to minimize time to money, which is time to market. And that factors into how fast you can bring capacity online. In order to conduct that, it's going to be done in a way that you're going to be doing it 24/7 operations. You're going to create disruption in the capabilities you're going to bring in so you can continue to push the envelope of technology. You have to have a systemic, disciplined approach on how you do it, but there has to be the ownership to make this happen 24/7. And that's what our engineers and technicians do every day. And on the right-hand side, earlier I mentioned that we're a very largely complex, cross-matrix company. You can't do it all alone. You have to bring along the industrial engineers. You have to bring along the facilities, the design, the factory design, the construction, in order to put these factories together and ensure that you optimize the overall outcome. So we'll probably open it up for questions, but these are my thoughts for you with regards to whether it's the people, the leadership, or the aspirations that you have in the career you want to pursue. Find your North Star, commit to it, and make sure that you have fun. The semiconductor industry is exciting, but it also could be like a roller coaster. It's cyclical in many ways, but also the innovation and complexity. That's why I've been there for 25 years, and I hope to continue for another decade or two. God's willing, and hopefully Intel will keep me around too. All right. Thank you so much. We can open it up for questions. Thank you.
Could we invite Jessica and Walt to stand up and just introduce yourselves to the students? Bear in mind, we have this room after the end of the class, and these folks will be around to answer questions.
Hi, everybody. My name is Jessica Voss. I'm the Campus Relations Manager for Intel here at Purdue. So what that means is that it's my job to understand our talent needs, what we're looking for, what we're hiring, where we have those skills and those people talent needs, and then come to campus and create opportunities for you to engage with us. I know many of you are first-year students thinking about what is coming in your career. Look for us back on campus again in the fall. We come to campus a couple of times. We engage with you. We're ready to answer your questions, and if you ever need anything, I'm always happy to help you. So nice to meet you all.
And good afternoon as well. My name is Walt Williamson. I'm also part of the Human Resource Organization at Intel, specifically talent acquisition. So in my role, I get the opportunity to lead our global campus recruiting organization, so interacting with students across the globe to help them find internship and full-time opportunities. In addition to that, I also lead the intern program team in the US and in Canada as well. So all of the incoming interns kind of go through a very similar corporate type experience that my team facilitates, in addition to the great experience that you get to go into within the business unit that you're a part of as well. Last but not least, my role is also the talent acquisition strategy leader for Ohio. So working very closely with Mutaz and Mutaz's team to make sure that we have the workforce to support the 3,000 jobs that we will have once the Ohio site is up and operational as well. So thanks again for joining the session today. And again, we'll open it up for Q&A, I think, with Mutaz and then Jessica and myself as well.
Awesome. So I'll ask one of our pre-selected questions as well. If you wanted to raise a hand, if you wanted to ask a question in the class. So given Intel's focus on AI and machine learning to enhance semiconductor manufacturing, how do you see AI evolving in this space over the next 5 to 10 years? And what role will data scientists play in these kind of transformations?
Wow, that's a really great question. I can tell you that machine learning has been deployed in the factories for a long time. There's statistical process control, automated process control, and closed loop feedback systems in the manufacturing. But if I were to use an example with regards to how we can see some of the AI tools helping us, there's something in the factory from an operation point of view. I'm not an AI engineer, but I'm going to answer it from an application perspective, where there's something called green to green. You have capital equipment that is very intensive capital-wise from a financial investment. And there's a green to green, means that when you're a green light, that means the tool is ready, available, and it can run silicon. When it goes to red, that means that capital, millions of dollars, is sitting idle and it's not doing anything for you. It's not being productive. We want to get the green to green. We're going to bring that tool back to green in the shortest time possible. How can we make that happen? We rely heavily on our engineers to troubleshoot and our technicians to do the troubleshooting and repair. For example, a robot is crashing a wafer, or a wafer just fell off the robot, or a chamber, the pressure signal is off. Something is wrong with the tool, that it's not producing the quality that we expect. Now the tool is down, you want to bring it back up. Where I see that the AI and machine learning tools could help us is, how can we take all the heuristics information that we already have and all the data and access to the data that we have, the information that the technicians have done in the past where they may have done the troubleshooting and fixed the problem previously, how can we take all that information and make it readily available such that the technician can use, it's almost like having an AI buddy, tell you exactly what you need to do to bring that tool back up, because this type of scenario has happened in the past. So that's one way I would see that could evolve over time. That's already being deployed, but I think we should be seeing that more and more pervasive in the factory.
So anyone, the next question?
Yeah.
Thank you so much. I don't think it's working. But my question was, you said Intel is an end-to-end firm, so they start from design, manufacturing, all to the end. Similar to the problem before, how do you ensure who holds responsibility during these processes? Because it's extremely precise distribution, design, so how do you ensure who's responsible, and how do you ensure all the products that are being manufactured are at the highest precision?
That is a great question, and I think if I could go back to that one slide, right? Let me see if I can go back to it. This right here. In a very highly complex and complicated business like semiconductor at Intel or even other areas. For Intel, it's more unique for us. Why? Because we are doing it from product from end to end, and it's an integrated device manufacturer. It takes, now remember when I said something about the people, the culture, and the values? You have to ground yourself in those values and principles, or how you behave as a company and how the people work with each other. Then you have on the right-hand side, you see that says partnership through collaboration, integration, and system synthesis. There's 4 diagrams on that right there, and that diagram is basically, you have this here where everybody, if one of these wheels falls off, it doesn't work, right? So we all make commitments on what it is that we own, and that's where extreme ownership comes in. We make commitments, we got to follow through on our commitments. Then also this right here, if you guys heard of the OODA loop, deploying the OODA loop, basically observing and understanding the environment you're in, because things are constantly changing. One thing constant in semiconductors is change, because it's happening all the time. And the decisions that you made yesterday or a month or a quarter ago or a year ago may not necessarily be the right decisions at the moment, and you may have to pivot very quickly. And that's the observation and decision-making process you have to have. You also have to have discipline and a systemic way of solving problems and communicating and working through across the integration of all the silos, right? And then everything will give you a nice, beautiful, integrated process and outcome. Does that help?
Yes, thank you.
Yeah.
So obviously,
If I may, the microphone for the students on the remote side.
okay.
The recording. So
Oh, it was good.
Even though, just speak to it.
So obviously, like, this is something like chip design and stuff that's very innovative, like year after year. And for us, because most of us are graduating in like 4 or 5 years, how would you suggest that we keep up with recent tech trends and kind of learn, every month, seeing that we're not in the industry right now?
That is a great, great question. For that, as you are going through your journey, let me go this right here. Curiosity, right? So you gotta love, that's one thing that I encourage all of you, is be curious. Ask a lot of questions and seek information. There's an Arabic saying that says, seek knowledge even if it's in China. But that was in the 7th century, because at that time, China was considered, I think, the most advanced civilization, and the distance from the Middle East to China was so far that the saying in Arabic says, it doesn't matter how far it is, but seek knowledge. But I think that's we go through curiosity. That's what I encourage you to do. And by the way, the information is all available to you thanks to Intel and semiconductor industry, because it's all there in the digital library, right? And also engaging, leverage other platforms, professional platforms, reaching out to folks in the profession. It's okay to put yourself out there. If you're curious, ask a question. The worst thing that can happen is the person never responds to your text. Even like, let's say you did it on LinkedIn, for example, as a professional platform. Put yourself out there and ask the question, right? It's a curiosity question. I can tell you, take my name down. I'm happy to converse with you on any topic that you like. I'm very opinionated, by the way.
I have a question about the. I have a more technical question. So, what innovations in like transistor architecture, power efficiency, and like manufacturing techniques is Intel going to use on 18A to further itself for Moore's law, like to maintain the standards of Moore's law?
That's a great question. So again, I'm not a transistor physicist, but I can tell you on 18A, I think we have backside power is the new feature that we're putting in. Obviously, there's Moore's law of the shrinking of the features and fitting more transistors in the same area. And we have also EMIB and Foveros, which I think you saw in the videos, some of the packaging technology on the back end. But I have limited knowledge when it comes to the device design, right? But I do know that backside power is a big deal, and that's a new feature for us that's going to help us with the new products. There is a 60-second segment that Intel recently released with regards to what 18A is all about. I encourage you to take a look at that. It's called 18A in 60 seconds.
I may have set that as a pre-read.
Oh, okay, there you go. That will tell you what the latest innovation on 18A.
Well, everyone, I'd love to thank the team from Intel and Professor, particularly our guest.
Thank you so much, guys. Appreciate it. Thank you.